Okay, good morning. My name is Bronikowski. I'm in the Department of Biology, Chemistry, Physics, and Mathematics at Northern State University in Aberdeen, South Dakota. I'll be talking to you today about chemical equilibrium and various concepts that come into play when reactions don't go all the way to completion. Okay? Now remember when we studied kinetics, we saw that many chemical reactions do go all the way to completion. Okay, so all the reactants, or at least all the limiting reactants, will react to form product. And an example of that we studied in our kinetics chapter is this one. It's the rearrangement of methyl isocyanide to form methyl cyanide. And we saw that this is a first order reaction. And if you monitor the concentration, the pressure of methyl isocyanide as a function of time, you'll see this kind of exponential decay curve, and the concentration gets lower and lower as time goes on. And we know from the shape of that exponential decay curve that as time increases without bound, as time goes out to infinity, this concentration is eventually going to get down to zero. Okay, so eventually, all of our reactant will react to form product. Okay, and many chemical reactions do this. However, not all chemical reactions run to completion. All right, it's not uncommon to find a chemical reaction in which, after a certain point, the reverse reaction begins to occur to an appreciable degree as the products build up in the reaction vessel. Now, an example of that is shown on the next slide, so consider this reaction. We have dinitrogen pentoxide reacting with itself. Two dinitrogen pentoxide molecules react to give us 4 NO2 molecules and 1 oxygen molecule. Okay, and this reaction will happen at room temperature in a vessel full of this gas. It can be monitored by the changing color as these molecules changes these molecules. Okay, and if you look at the concentrations of the various reactants and products as a function of time, and this is plotted here, I've got time on the x-axis and a general concentration variable on the y-axis, and if you look at the concentration of N2O5, you'll see that that decreases in some kind of an exponential kind of way, as we've seen for a regular reaction that goes all the way to completion. And if you look at the products, you'll see that they start building up from 0, and the product concentrations increase with time. So, okay, so far that looks like a normal reaction. What you see as you continue monitoring is that this N2O5 concentration does not go all the way down to 0. After a while, it kind of levels out, and it reaches a point where it no longer changes in time. And likewise, monitoring the product concentrations, you'll see that they increase up to a certain point, and then they get to a point where those concentrations no longer change in time. So it looks like what's happened is the reaction goes to a certain point and then stops, and you get no more formation of products from the reactants. Okay, now what's really happening here is that as the NO2 and the O2 concentrations increase in the reaction vessel, the reverse reaction begins to occur. Okay, and that's shown here. You get 4 NO2 molecules reacting with 1 oxygen to form 2 N2O5 molecules. Okay, so you get the reverse reaction starting to occur, and eventually, as the concentrations of the NO2 and the O2 build up in time, you reach a point where the rate of the reverse reaction is equal to the rate of the forward reaction, and at that point you get no net concentration, net change in concentrations with time, because you're forming N2O5 molecules as fast as you're consuming them. You're consuming your product molecules with the reverse reaction as fast as you form them. So no net change in concentrations with time. Okay, now this is really just an example of something we've seen before, what we call a dynamic equilibrium. And remember, this is something we first studied when we studied vapor pressure. Dynamic equilibrium occurs when two opposing processes in the same system proceed at equal rates. And again, the example we saw was just the establishment of a vapor pressure in gas phase above a liquid phase material. So you have two processes going on: evaporation, where the liquid molecules go into vapor phase, and condensation, where the vapor molecules come back into the liquid phase. And if you start this out when you just have a vacuum up here, you get a certain evaporation rate, and you get very little condensation rate because there are very few molecules up here to condense. But as time goes on, the density of molecules in the gas phase build up. The rate of condensation increases because you have more molecules up here trying to condense, and eventually you reach a point where the rate of condensation is equal to the rate of evaporation. So you have these two opposing processes, molecules going from liquid to vapor and vapor to liquid, occurring at equal rates, and it looks like what's happening is no change is occurring. But in fact, both processes are still going on, and you've reached what's called a dynamic equilibrium, where the two opposing processes proceed at equal rates and exactly cancel each other. In this case, we call the vapor pressure reached here the equilibrium vapor pressure, and again, this is just an example of a dynamic equilibrium. Well, that's basically what we see going on in a reaction of this sort. We have a reaction, the reactants going to products, and products going to reactants at equal rates. So forward and reverse reactions happening at equal rates. We have a dynamic equilibrium between reactants and products. Now in chemistry there's a special name for this kind of situation. That is called a chemical equilibrium. And it occurs when the forward and reverse reactions are proceeding at equal rates in a system. And in equilibrium, it looks like nothing's happening because your concentrations are not changing. But in fact, both reactions are still occurring. It's just that the net concentrations aren't changing in time because the reactions are proceeding at equal rates. All right, and again, it's common to find chemical systems which don't go all the way to completion, as is shown here, but in fact only go until some equilibrium point is reached, and then you won't get any more production of products from your reactants. Okay? Well, an interesting question in that situation is, what are the concentrations of the reactants and products when the system is in equilibrium? If you're dealing with a reaction that doesn't go all the way, okay, how far does it go? How much products will you get? How much of reactants will you still have around? That's what we're interested in. And we can start to get an answer to that question just by considering what I've drawn here is just a sort of a general purpose, general reaction. You have A and B in gas phase going to form C and D molecules in gas phase. And I'm saying that this is a system in equilibrium, so you also have the reverse reaction, C plus D going to A plus B, at some appreciable rate. I've actually shown that by drawing arrows here going in both directions to show that both the forward and reverse reactions are both occurring. Okay? Now remember what we learned when we studied kinetics. If both the forward and reverse reactions are single-step mechanisms, okay, that just single-step bimolecular reactions, then we know something about the dependence of the reaction rate on the concentration. For single-step mechanisms, we know that the forward reaction rate has to simply be proportional to the concentrations of A and B raised to the first power, because we only have one molecule of each here. And we can write that forward reaction rate as some constant, K forward, times concentration of A times concentration of B. And similarly, we can write the reverse reaction rate as some constant, K reverse times concentration of C times concentration of D. Again, we know this to be true because we saw in kinetics that for single-step processes, the reaction rate depends in this way on the reaction concentrations raised, in this case, to the first power, because we only have one molecule of each in our balanced chemical equation. Okay? So we know what the forward reaction rate is, we know what the reverse reaction rate, and we're saying in equilibrium, these two rates are equal. Well, if we just set these two expressions equal, we have our constant K forward times A, concentration of A times concentration of B is equal to K reverse times concentration of C times concentration of D. With a little algebraic rearrangement, that becomes CD over AB, all concentrations here, is equal to this ratio, K forward divided by K reverse. Now these numbers, remember, are both constants. They don't depend on the concentration. They can depend on the temperature. And that ratio we can just rewrite as another constant, which I've denoted here as capital K. So in equilibrium, when the forward and reverse reaction rates are the same, it must be true that this number, product of C times D divided by product of A by the product of the concentrations A times B, has to be equal to a constant. Okay? So what we've seen is for this kind of a model system, in equilibrium, all the concentrations of these reactants and products must obey this equation for some constant K. And all of this falls out of basically the definition of equilibrium, the fact that the forward and reverse processes are balanced. This rule is a very important rule in chemistry. It's called the law of mass action, which states that in equilibrium, this ratio will remain constant irrespective of the individual concentrations of the individual reactants and products. This ratio, the product of these concentrations divided by the product of these concentrations, will remain constant. Now, my argument that I've given you only applies in the case where both the forward and reverse reactions are elementary reactions occurring in a single step. It can be shown algebraically that the same is true even if one or both occur with multi-step mechanism. The algebra gets a little bit hairy. I'm not going to try to show you that here, but it can be shown that this law, this equilibrium law, holds even when the forward and reverse reactions are both multi-step. Now, more generally, again, what I've shown you here is just one molecule of each reactant and product in this equation. More generally, the law of mass action states that for an equilibrium in a reaction of this form, where each of our reactants and products has a numerical coefficient, that the law of mass action will look like this. So if we have multiple molecules of A and B reacting to form multiple molecules of C and D with the coefficients given by our balanced equation, this ratio is going to be a constant. So the concentration of C raised to the power of Y, the coefficient of C in the balanced equation, times the concentration of D raised to the power of Z, and then divided by the concentration of A raised to the W power, times concentration of B raised to the X power. So each of these concentrations is raised to the power of its coefficient in the balanced equation, that this ratio is equal to a constant. And again, that's just the law of mass action for your general chemical reaction, which is known to be in equilibrium. This ratio will be a constant. Now, this is a very important expression in chemistry. It basically describes all equilibrium processes. This is what is known as an equilibrium constant expression. And this constant Kc is what is known as an equilibrium constant. And what this is telling you is that for any chemical system in equilibrium, irrespective of how you may change the concentrations of any individual reactant or product, the system will always rearrange itself so that this ratio is a constant. And this is really the key concept for understanding and working with systems in equilibrium. Okay, thank you very much. Any questions?